Good day, everyone. My name is Marcus McCammon, and I am the president of Ricardo North America. First and foremost, let me thank you for joining us today for our latest webinar on activating your connected vehicle data. As we all know, the global automotive space is changing. Software and connectivity are becoming more prevalent, and they're going to define the value proposition of our vehicles going forward into the future. We know that vehicles have to be connected. What we don't necessarily know or agree upon is what the right way is to enable that connectivity and make sure that we're getting the best access to that data when we need it, such that we can create new value propositions for our customers and a new business stream for our internal businesses. That's what we're going to try and start in on today. It's a very big topic, but to help me get through the topic, I have two of our core leaders. First of all, I have Madison from our tech and strategy team. Madison, can you introduce yourself, please?
Thanks, Marcus. Yes, I'm a part of our technology and strategy team, focusing on software solutions for the connected, automated, and autonomous driving space. That encompasses connectivity solutions like cloud to car, V2X, vehicle to anything communication, as well as the embedded software offerings that are going to enable our next generation connected and autonomous driving vehicles. Today, we're going to be focusing on really the value of connectivity and connectivity services and leveraging the data that we can extract from these connected vehicles.
Excellent. And then also, we have one of our key brains in the software space, Pete. Pete, can you introduce yourself, please?
Hi, I'm Pete Brown. I'm Chief Software Architect here at Ricardo. I have a broad background in many aspects of software, including real-time operating systems, real-time embedded devices, open source software, Linux, Android, cloud compute applications. I've spent a number of years looking at architectures related to consolidating ADAS solutions and what the next generation of architecture should look like for autonomous vehicles. Of course, you can't do any of that without vehicle connectivity, whether it be high definition maps, V2X technologies. And today we're going to talk about a number of those areas where data and data collection, getting more data out of your vehicle, and not doing it in a wasteful manner, trying to target what data is really needed and not overloading back-end systems and making use of the right layers of compute technology to achieve that.
Thanks, Pete. Thanks, Madison. So before we get into the bulk of our agenda for the day, let me start off by giving you an overview of who we are as Ricardo and Ricardo North America. Firstly, Ricardo is an organization that's been around for over 105 years. Since its start, Ricardo has been focused on the transportation industry, looking at propulsion systems and trying to figure out how to make those systems more efficient and cleaner. As we've evolved over the past century, we've incorporated aspects of environment, looking at transportation from an infrastructure standpoint, as well as looking at how the business of transportation impacts the community in which it exists. Today, we exist as a business that can service that industry from end to end. In total, we're about 3,000 associates across 51 sites and in 20 separate countries. Our business is broken into divisions that support discrete aspects of the transportation sector and its surrounding ecosystem. Starting first with the Energy and Environment Group. Energy and Environment really looks at how vehicles and systems are going to interact in the world space, what are going to be the factors that impact the decisions that we make, and what are the downstream implications of those decisions. Things like air quality, water consumption and water usage, water scarcity. Where does fuel come from, and what kinds of fuel have positive or adverse impacts on the environment? We also look at rail, as rail is a means of getting materials across long distances and people inside of small spaces moving very rapidly and efficiently. At the core of our business is our automotive and industrial group. That's really where the business was founded. And automotive and industrial touches everything that moves both on highway, off highway, and in the air, and generally in the way that we think about moving people and materials. We have a defense sector that really focuses on direct interaction with the Department of Defense here in the US. And between defense and our automotive and industrial group, we work with defense contractors both directly with the DoD as well as with the primes to support the infrastructure for defense, both here and abroad. We have a production group that really focuses on low volume, really hard to manage production instances. Most famously, we're known for being the engine maker for McLaren. But beyond that, we do low volume production programs across multiple sectors of the transportation space. Next is our software group. Software really looks at how do we create and integrate better tools to make the design process more efficient and more robust so that we can shrink the time to market and improve the quality of product delivery. And last but not least is our consulting group that looks across multiple sectors to look at how the business implications and the environmental implications come together to make better decisions to support our customers. Here in North America specifically, we focus on a charter of integrating a path to a better mobility future. Today, we have a very fixed construct of what transportation looks like, and it's usually built around the internal combustion engine. Tomorrow, our portfolio is going to be much more diverse. We'll have electrification, we'll have hybrids, mild hybrids, and everything in between. We'll have vehicles that are purpose-built and driven by the consumer, and we'll have vehicles that drive themselves. Our job is to help bridge the gap between today and tomorrow, and to make that bridge more efficient for our customers, such that they can transition into that new promise more effectively, more rapidly, and with the proper support that their consumers are looking for. The key word in this discussion is mobility. And for us, mobility means transportation that is enabled with data, which is a key lead-in to our discussions of today's meeting. In terms of how we do it, or what we do, we look at separating our business into three core sectors. On one end, we have propulsion and all the many facets of and definitions that will encompass propulsion as we go forward. On the other side, we have software. And in software, we look at everything from fixed controls to autonomy, and then ultimately the notion of creating a digital twin where we can model our physical environment in the digital environment and have the two connect with each other such that the process of designing is done more rapidly, but without loss of robustness. And in the middle is thermal systems. As we embark on new kinds of transportation and more efficient transportation, we will call on those propulsion systems to run more aggressively, to run more efficiently, to run more rapidly. We'll incorporate batteries and controls and electronics. We'll add high power compute. All of those things will drive heat and load into the vehicle. And if we want the vehicle to be able to meet the needs of the next generation of consumer, both in range and speed and time and performance, we need to balance the entire vehicle system and make sure that we're thinking about the thermal implications of that vehicle as well as the discrete subsystems that make it up. Like I said before, we are a global business. So we're not just looking at these matters in one sector or in one regional area. We're looking at them globally. And we've been doing this for over 100 years with a veritable who's who of members of the transportation ecosystem. This is just a small cross-section of some of the customers that we worked with. And as we go forward, we look to incorporate our learnings from all of these different disciplines and all of these different sectors that to inform our decisions and inform our recommendations to our customers to make them more robust, which all leads me to our discussion for today. Today, we're going to focus on software and how connected and autonomous systems are going to evolve and how data and connectivity will enable those systems to evolve more rapidly and what we can do to make that better. To help us with that topic, I will hand the microphone over to Madison. Madison, why don't you take it away from here?
Thank you, Marcus. Now we're going to jump into connectivity technology trends and the benefits of leveraging the technology as well as the data that we can extract from connected vehicles. To start, we want to focus on this accelerated rate of change of this new automotive world. Traditional automotive had a slow overall innovation rate, but when you're combining technologies, the IT systems or software suppliers, we're looking at this highly accelerated rate of change encompassing connectivity, automation, and the benefits of those functionalities. And what's really driving this accelerated rate of change, as well as the benefits provided by the technology, is the software and electronics, the services and connectivity that's provided by these next generation connected, automated, and autonomous driving vehicles. Some of the technology trends that we're really focusing on at Ricardo, but globally in the transportation automotive space, the first being safer, automated, and autonomous driving systems. This is all the way from level 1 to level 5, really encompassing the advancements in connectivity from V2X, IoT, as well as the introduction of the mobile device to the car, over-the-air updates, and other connectivity services. And with that connection is an immense surplus and increase in the amount of data that's generated not only from the devices that we're bringing into the car, but the vehicle itself and the way the vehicle is interacting with the surrounding infrastructure and cloud systems. So this, the advancement in technology is not just giving us opportunity, but it's really increasing the amount of data that's available to us. And finally, to realize the benefits of these new technologies and services and actually make them come to fruition, there is an increase in the amount of compute power that's needed within the vehicle, as well as in the surrounding infrastructure, as well as in the cloud and data centers to really harness the power of the data that's coming from these connected vehicles. And really what's driving these trends and the advancements in technology is a convergence of software solutions from connectivity through automation, autonomy, the electrified embedded system, as well as electrification of the propulsion system, all the way through to mobility. The innovation here is in the software and electronics and the services that are surrounding those new technologies. And with the introduction of this innovation, new software, there's increase in software components in the car, but also the complexity of the software solutions. It's increasing opportunity in the new features. So we're having highly autonomous cars, electrified, new data, new services, but it's increased risk because of the amount of connection to the vehicle is also increased. And really focusing here on what the differentiation is being provided. It's a shift from value in the vehicle being defined by hardware and mechanical components to an evolution of the value being driven by software, connectivity, and the services surrounding those technology advancements. So for this webinar, we are discussing connected vehicle technology advancements and the ability to and how we can best leverage the data that is coming off of these vehicles. So first, if we start discussing the types of connected vehicle technologies that really enables us to take advantage of this data, it's first starting with embedded connectivity. So the car has now become connected to the cloud. We can extract vehicle data. We can also push new services to the cars. The vehicles are now connected not only to devices that are brought into the vehicle, but to other vehicles surrounding infrastructure. So it's really this highly connected system of systems and infrastructure to vehicle connectivity. There's also additional sensors and sensing capability that have been added to the vehicle. So the types of data and the amount of data that these vehicles are generating is increasing. Now, if we take a look at the shifts and overall architecture of the embedded system as well, we touched on the evolution of compute and the computing needs within the vehicle, as well as cloud compute, to really take advantage of the benefits of these new technologies. So the transportation industry is seeing an overhaul of the ECU architecture, the way that the functions and services that are integrated into the vehicle are managed. So it's no longer one function, one compute, but the functions within the vehicle are enabled as services. And the cloud has been brought into this integration and communication within the vehicle as a service. So it's not just an evolution of the vehicle connectivity, but the embedded system as well. And beyond that, to enable the connectivity advancements from car to cloud, and really see the value of these intelligent traffic systems, you're seeing an evolution of the infrastructure system as well. It's heavy investment in cities, government bodies. You're seeing several smart city initiatives to really bring in the innovation, not just from the OEMs and the tier 1 suppliers, but the whole software supply chain, as well as smart cities and government, to really make this come together. And an incorporation of external organizations and other bodies that really bring it all together. So we need cybersecurity specialists. We need legislation in place that manages the introduction of new software solutions in this space to make sure that they are adhering to the right safety, security metrics to make it viable for these next generation connected autonomous vehicles.
So Madison, you outlined a lot of moving pieces that are in play as the transportation space is transforming. Infrastructure, the vehicles, the data systems. How do we rationalize the fact that not everyone's going to be able to move at the same pace?
That's a great question, Marcus. Really what we need is members of this supply chain, the OEMs, the tier one suppliers, and the system integrators to really take a systems view, to have an understanding of where we've been, where we are, and where we're going, and to make sure that we're engineering our embedded systems as well as the sensing capabilities with an idea for the future. For example, we can take Tesla that's been able to unlock new features, new functionality, new services over the life cycle of the car. They've enabled battery extension in the event that a natural disaster happened. So they've really taken this systems view, but also architecting their solutions with security in mind and the compute power in mind for longevity.
Thanks, Madison.
So that's a great segue into our next topic, which is discussing the benefits of connected vehicle technology, data, and connected services throughout the entire life cycle of the car. Starting from cost reductions, the enablement of new safety and security features, as well as new revenue streams throughout the entire life cycle of the car. So if we take a look at overall cost reductions, we can really leverage connected vehicle data to establish a real-time feedback loop back to our engineering teams. And this is cross-vehicle type, make, model. But you can leverage learnings from either development data or production vehicle data to enable better designs, more cost-effective designs, and getting those new features and new services incorporated into next generation designs faster or deployed out to production vehicles faster and at a lower cost. Connected vehicle data and connectivity services enable us to remotely pull data, but also push services to the car. So we can leverage over-the-air updates to eliminate software-related warranty recall costs. So we no longer have to bring our cars into the service bay, but we can deploy software updates and eliminate the technician, eliminate the impact of brand image, and the cost of that warranty recall. And then finally, we can reduce warranty bills and enhance our maintenance strategies by enabling fault prediction, proactive and prescriptive maintenance, and then really reducing the number of unpredicted mechanical failures. So reducing overall cost of ownership and downtime of our commercial fleets. And now if we look at this from the safety security perspective, connected vehicles allow safety critical data and warnings to be shared in real time, not just to other vehicles, but to emergency services and to infrastructure as well. So we can reduce the number of accidents, improve emergency response times. With driver monitoring, we're actually able to monitor the driver behavior when they're leveraging automated services. We can improve road designs, and we can also improve the safety functionality and mechanisms within the car at production through the entire life cycle of the car through a security patch, through software updates. So as the hackers get smarter, so do our vehicles. And finally, when we're looking at improved revenue streams, the point of sale is just one mechanism for revenue generation for the OEMs at this point. And they can actually have more aggressive pricing strategies at production by monetizing new services and functionality over the life cycle of the car. So OEMs can deliver additional services post-production. They can unlock existing functionality within the car. A great example is the Tesla Autopilot, where they enabled drivers to purchase autopilot functionality post-production at a premium. So really the OEMs can monetize these new services and new functions, not just at the point of sale, but through the entire life cycle of the car. Now, to realize the benefits of these new technologies, whether it's cost reduction, improvements in safety security, as well as the new revenue streams, the solutions must address a broad spectrum of challenges. So the next section really covers challenges and considerations. We have broken down connected vehicle challenges into 4 main sections. First, starting with connectivity availability. Connectivity availability is heavily driven by connected vehicle type, whether it be a passenger car, commercial vehicle, or on the far contrast is the heavy machinery or agriculture vehicle, heavily impacted by the geolocation of that vehicle. So whether it's in an urban or well-established city environment, or open field, or even a military vehicle that has no available connections. And finally, the usage, the driver usage and preferences. So you can compare a lower end passenger car where the data is only collected when it's brought into the service bay. And the amount and frequency of data that's able to be pulled is really heavily dependent on how often that driver brings their vehicle into the service bay. And compare that to a high-end luxury car, which not only is continuously connected, but it has additional sensing capability. So lots of connections and availability is high. And then on the far end of the spectrum, you can consider a military vehicle where the connection availability is quite low and the impact of mechanical failure is extremely high. So moving forward, we need to consider data frequency, fidelity, how clean and accurate the data is. There are well-established methods for collecting diagnostics and telematics data, as well as typical OBD solutions, but these may not provide a ready access to raw, high-resolution sensor data that we want. So the solutions that we deploy really need to address frequency of data collected, fidelity, and resolution of the data that we collect. We must also consider bandwidth restrictions, whether that's the in-vehicle network, so the CAN bus, Ethernet networks, or it's the car-to-infrastructure, car-to-cloud. We need to enable really targeted data collection strategies to minimize the impact on the bandwidth, but also decrease the latency and the time required to pull data off of these connected vehicles. And lastly, but certainly one of the most critical areas that we need to focus on is safety and security. And this means that we need to ensure that the points of connections established on these vehicles are not also enabling the introduction of malicious code to the vehicle and not allowing hackers to tamper with the data that's pulled off the car. We also need to be leveraging the ability to deploy new services and functionality to deliver security patches and upgrades to the security mechanism from the car over time. Ricardo is taking a systems holistic view at the connected vehicle data pipeline, ensuring that our customers' data collection strategies account for the broad range of challenges that we just discussed. So this slide really is a high-level view of the Ricardo approach to data activation. And by data activation, we don't just mean pulling data from collected vehicles, but really leveraging data collected to enable those cost reductions, the safety and security enhancements, as well as the new revenue streams that we just mentioned across the entire life cycle of the car. So instead of pulling any and all available data from the connected vehicles, we focus on targeted data collection strategies to reduce the amount of data collected, reduce the cost of transfer, and the amount of data to be analyzed. So we're ensuring that we're really pulling data with a purpose. We analyze where to store the data, what pre-processing is necessary, whether it's done on the vehicle at that fog architecture level or in the cloud. So we can optimize the cost, the time, and the amount of data that needs to be transferred from the car to cloud. We leverage AI and machine learning to intelligently detect anomalies and enable not just prognostics, but to reduce the amount of manual engineering effort to analyze the data. And we've been working with vehicles for over 100 years. So we really know what connected vehicle data is telling us. We know how vehicles can fail, and we know what's needed to distribute the resolutions for those mechanical or software failures. So, and finally, and this is a component that we touched on earlier, but we know how to architect embedded systems, not just the underlying compute, but those integrated software platforms to enable the incorporation of new features and services post-production. So not only can Ricardo help you detect faults and provide solutions to those impending software or mechanical failures, but we can also help our customers to find secure and cost-effective mechanisms for delivering those fixes or new features to the vehicle at the design development stage, through production, all the way through end of life. So I'm going to pass it to Pete now to cover the IoT architectures and solutions to really realize the benefits of connected vehicle technology and the data that we're pulling off these vehicles.
Okay, thank you, Madison. Now we're going to talk a little bit more about the architectures, some of the challenges involved in the connected vehicle and how to get the data out of the vehicle in the best manner. Of course, we have a lot of challenges with respect to whether you're collecting the right data at the right time, how much data, the amount of bandwidth that you're using, how many vehicles are being broadcasting data up into the cloud, and what kind of bandwidth constraints that has on that data being sent up, and of course, respective costs that surround that. So first, let's talk about how the data can impact certain use cases. And Ricardo has engaged with OEMs on a number of projects where we've been able to take the engineering expertise that Ricardo has in our legacy of knowing engines design problems, the types of problems that can result, what sensors, data the sensors collect, what that sensor data looks like, and especially when you have access to high-speed data, when you have that kind of off-board diagnostics capability, the ability to tap into high-speed sensor data, what that data means, what's happening to the engine. It might be vibration related, it might be a flaw in software. However, some of these engagements that we've had with customers, we've really been able to help them understand what's going on inside the vehicle, and in a number of instances, been able to analyze that data and be able to save the customer an awful lot of money in terms of avoiding things like engine replacement. So in this instance, it was an OEM where we found that if we could monitor what's going on with oil pressure, if it passes the oil pressure test that everything was fine, just continue on with the service. Otherwise, hook up some diagnostic tools, do some additional tests, and based on the data that you get from that, you can decide whether, or at least go through the process of making the decision of whether that customer needs to have their engine replaced. Another example here was with effectively connecting rod bearing failures. We were able to determine the typical signatures. So from a knock sensor, which effectively, type of vibration sensor data, you can see the normal kinds of vibration signatures that are emitted when everything's okay. But we were able to determine that certain vibration characteristic signatures were evident in the engines where the connecting rods were starting to fail. And so the failure of the connecting rod was actually highlighted by NHTSA as a potential safety problem. Of course, if the connecting rod goes while somebody's driving down the road, it may spook them, it may cause them to do something erratic and do something unsafe. However, of course, the OEM doesn't want to just go ahead and replace all the vehicles which have this type of engine. But what we were able to do was effectively help them understand the signature of the vibration of these engines that were exhibiting this problem. And they were able to send an over-the-air update to the engine ECU in the vehicle to look for that type of signature on the knock sensor. And therefore, if you detect that type of signature, you go into a limp hone mode and enable the customer to take their vehicle safely to a service center. And then via additional analysis, just choose to replace the engines on only those vehicles. Again, that's saving a recall and just replacing all the engines of all the vehicles. So that's great when you have the ability to have high-speed data that you're able to analyze and come up with like the previous example, you have connecting rods and they exhibit a certain type of vibration signature, but you get that from very high-speed data. And that's good in a development environment. I know a lot of OEMs, they're able to accumulate an awful lot of data, high-speed data of what a good engine looks like, but they only can do it on a few vehicles, just the vehicles that they have immediately. Of course, once those vehicles go on sale, you have the opposite happen. You have the inability to capture that high-speed data, but you have a lot of vehicles that can provide data. And so is there a possible means of getting a bit of the best of both worlds, having the ability to do the types of off-board diagnostics, but do it still within the car? Now, I've seen some architectures where the OEM is effectively making requests directly from the cloud to the vehicle, capturing as much data all the time, sending it up to the cloud. When you do this, of course, you're accumulating large data sets. You have lots of customers, lots of vehicles out on the roads. And if you're really just collecting everything all the time, you're not necessarily capturing just the data that's needed, maybe only under the circumstances with which it's needed. And that this incurs a high data usage and a lot of data transferring up to the cloud that may not be needed. So how do we mitigate against that? And what I look towards are things that you would typically find more in the world of the Internet of Things in an IoT environment, where they introduce the different layers of networking and ability to process at those different layers of the network. So of course, in a typical infrastructure, you may have the application center, you may have third-party applications, you have your internet backbone, you have untrusted public networks, trusted networks, and then you kind of what you call the edge and the far edge, and then what we might call a fog layer, and then there may be also mist layers, if you will. And really what we're talking about is just different levels of communication between devices. You may have your far edge devices generating data, and given certain applications, if I were just to have all those far edge devices broadcast everything up to the cloud, you deal with the same problem. You have the cloud getting bombarded with tons of data that it may or may not need. And then from an application processing point of view, if I want to quickly do something with this data, the round trip time from data going from the device to the cloud, processing some algorithm, making decisions, sending some signal back to the edge, could incur a long latency, and it might actually be too long to fulfill the needs of the application. So this is where you get into the fog layers, where you have some kind of processing capability closer to the edge devices that can take that data, do some lower latency, lower jitter type of performance processing, and react to the needs of the environment as necessary, filter that data, and then only send up to the cloud that which is needed. Now, in terms of the car, really what we're saying is that the edge is the car, and the far edge is the ECUs, and the very far edge might be the sensors connected to those ECUs. A lot of the time, those sensors are broadcast onto the vehicle CAN bus. Other sensors, like vibration sensors, that may be very high frequency in terms of the sampling by the software, maybe 20,000 hertz. That data often and is usually not put onto the vehicle bus. But there are mechanisms with which we might be able to get access to that data. As mentioned, we want to reduce, if we're looking to capture high quality data, high frequency data, we need to be able to communicate with those ECUs with very low latency, very low jitter, if we're going to make any sense out of the kinds of signatures that we get from that data. And we want to deal with all of that from a high bandwidth on the device side and lower amounts of bandwidth going back to the cloud. However, we only have so much bandwidth available in the vehicle. These pie charts that somewhat look like pizzas and pepperoni are really overall bandwidth available on a vehicle bus. The yellow may be your anti-lock brake system. The green may be your transmission, blue or engine and transmission. The red area is trying to represent available bandwidth. The red dots kind of represent the different sensors that you might be able to, that may not typically be broadcast onto the CAN bus, that we may be able to access via something like UDS, Universal Diagnostic Services, and query that sensor data at some rate to better leverage that available bandwidth in the vehicle. So we can do everything from one end of the spectrum to the other. The one end, on the left side, it's request sensor data uniformly across a whole number of sensors and a pretty uniform rate. Or on the other end of the spectrum, we can target just a few sensors and really request at high data rates those sensors and their values, and leverage all of that available bandwidth just to get, say, 2 or 3 sensors that we want to get as high fidelity data out of as possible. And then there's in the middle, where you may have a varied and wide mix. Maybe not all sensors, but some sensors that want to get more more data from than others. However, doing that from the cloud is going to be very difficult, especially if you're trying to go directly from the cloud to the vehicle and to the vehicle bus. And so what we really need is a more flexible in-vehicle application that can enable different sensor gathering strategies in a very flexible manner. UDS enables this. Part of the UDS protocol allows for different messages to different ECUs that support the UDS protocol. And one of them is this read data by identifier. The identifier is a parameter, can represent one of the sensors that's directly attached to the ECU. We can make this call at a higher rate and get something like vibration sensor data out of that ECU that typically isn't broadcast onto the vehicle bus. And we can do that in terms of as high a frequency as possible given the available bandwidth on that bus. Again, this gets us closer to what would be considered off-board diagnostics. Most of what gets broadcast onto the CAN bus typically is you're going to be your onboard diagnostics, usually around emissions. But when it comes to some of these other sensors, there's often OEM proprietary UDS messages that your typical off-the-shelf OBD port tool probably doesn't have the information to know which ECU, which identifier to use, what the data means when it comes back over the bus. So in a given use case, a company like Ricardo, with our expertise and legacy in engines and transmissions and the ability to do the analysis of the sensors and the sensor data, we feel that if you had an on-vehicle application which can take a dynamically created query, something that's just a text-based query that says, I want to get more information about sensors A, B, and C, but only start collecting data during specific circumstances. And the example given here is that the vehicle is at a certain altitude, it's a certain temperature, and maybe it's also when the operator hits wide open throttle. That's when I want to start gathering data, and I want to gather it from just the specific sensors just during that period of time. So the step number one may be, what's the problem the OEM's having? And our engineers would sit around, hypothesize, and somebody may end up saying, well, if I just had this extra bit of data that I could get from the vehicle, it'd help me understand the problem. So let me write this query. I'm going to just put a text-based query together where I can say I'm looking for these sensors under these conditions at these sample frequencies, send that down to the car. That would then be effectively initially just received by some in-vehicle ECU unit. It would not execute that query until the criteria that have been defined are being met. Once those criteria are met, it will start querying those ECUs within the vehicle and start gathering the types of data that are being requested by the query. Those could be stored locally, especially if cloud connectivity isn't available. Store it, and then once the cloud becomes available, send it up to the cloud, at which point our engineers can start analyzing that data. And of course, there's always the potential that you have an improvement to a piece of software to resolve the issue, and then you could send an over-the-air update down to the vehicle. And again, it's at least a potential to fix the problem. So the vehicle then really just does become a bit of an IoT device, following the kinds of architectures where you can process locally, do high-speed processing locally, and then enable that cloud infrastructure as necessary to process the data. And of course, you can pre-process the data before you send it up to the cloud. So you get cleaner data that was only just the data that you're looking for, only under the circumstances you're looking for. You reduce costs by sending less data to the cloud. And then, of course, once you have the data in the cloud and you're doing the analytics on it, you don't have a bunch of dirty data you don't need, data you don't want, data you need to try to filter and ignore on the back end. So one aspect that I always feel is very important to talk about when we talk about connected vehicles. We've talked about these different architectures, these different types of networks, the ability to communicate to the vehicle, get data from the vehicle. However, the aspect of cybersecurity is always one that is a bit of a passion of mine. Anytime I get an opportunity to speak on these topics, I do like to highlight the issue and continue to raise awareness as it is critically important for all of us. I think it's something we all need, we all expect, but at the same time, it's a little ambiguous in terms of whether you've achieved security and whether these types of systems are in fact secure. And really on this slide, all I'm trying to demonstrate or articulate is we go through an awful lot of effort in terms of the software that's in a vehicle to make sure that the software that's being run is in fact the intended software that we want to run. So we go through all these processes. We create these, software, we compile the software, we end up with these binaries. We do digital signing of the software. Then at runtime, the system boots up. It will check the digital signatures using public-private key encryption techniques. And we do that through the entire process of the boot up. So from the first stage bootloader to a second stage to the kernel and the operating system, file systems, all the way up to the application. We can do all of these checks, and that's great. We're effectively establishing a chain of trust across all of these executables, and we call it secure boot. That's great. However, we do not do the same thing with respect to our supply chain. There's a lot of third parties involved in the development of these connected technologies, these various services, and we integrate them together. And I think, when we take into consideration safety systems, the security analysis is actually, these days, it's part of that overall development model. We look at safety requirements and therefore we look at security requirements, because if you're not dealing with a connected device, if you're not secure, you're not safe. And so we do threat analysis and risk assessments, security requirements, implementation. We go through this V model. And unfortunately, of course, these things can increase cost greatly. But when you're not dealing with a safety ECU or safety considered to be a safety piece of software, you may not be adhering to the same kinds of security threat analysis and risk assessments that you should still be doing. And so you get this situation where you have a complex supply chain. You have the OEM at the top of the pyramid accepting software from the tier ones and the tier twos. At the end of the day, a secure boot process, if you haven't established a supply chain that you trust, then you're really only as strong as your weakest link. You need to make sure that the software deliverables that are provided by those third parties, that they provide evidences that they adhere to the respective security solutions or security development processes, so that you know what you're getting when you integrate it all together is going to be an overall secure system. And so you can see that. Yeah.
I'm sorry, Pete, can I ask you a question on that? So
Yeah, sure.
one of the things that I see with a lot of our suppliers in the transportation industry is, like you said, we have a very diverse supply chain. And in some cases, we try to focus our investment on components that are going to generate new direct consumer value in the current generation, right? And which means that we'll use components from prior generations that we leave relatively untouched. We don't modify them. That effectively turns into a cost savings model for us. So
Right.
if we have to now apply this thinking of cybersecurity to these legacy components, how do we balance that? Is there a way that I can only apply it to the new and not the old, or what are your thoughts there?
That is one of the perplexing questions I think the industry faces. Of course, as you mentioned, everybody wants to leverage reuse. When you have devices that were originally developed before there were connected vehicle requirements, cybersecurity probably was not really one of those things that was at least in depth addressed. And then, of course, you get the reuse over the years. Of course, engineers move on. Who knows what actually some piece of software is doing, and then all of a sudden that piece of software ends up in a vehicle which is now connected, and potentially at least has all of those legacy security vulnerabilities that come with it. In fact, when you look at any given vehicle, simply asking the question, how many parts in this vehicle have software and how many software vendors were involved in developing that software? It's a very, very difficult question, and really it's almost unanswerable when you consider this kind of pyramid where you have multiple tiers of suppliers. I think one of the things that everybody can do is architecturally develop layered security and make it much more difficult for an attacker to be able to take advantage of any one security vulnerability. Effectively make it so that even if you can take advantage of one, now you get blocked by another layer of security, and you'd have to effectively have an entire laundry list of security vulnerabilities lined up to be able to do anything of any significance. But the reality is, for the foreseeable future moving forward, that the software is going to have security vulnerabilities. And of course, as mentioned, if you're not secure, you're not safe. But typically with safety devices, as you move forward through time, the device proves itself to be more safe. The opposite is true is with security. As you move forward through time, you have the higher likelihood that security vulnerabilities in a given piece of software that has been used in the car does get exposed and could be exploited. But
So
I don't think
effectively, what you're
there's...
saying is, on a safety side, with time comes validation. That validation inherently supports the notion of safety. With security, with time comes obsolescence, and with that obsolescence comes the ability for vulnerability.
Right.
Gotcha.
Yeah, and of course we've even seen vulnerabilities in the silicon itself. So you don't know where it's going to come from, and that's really the big difference, I think, between safety and security. Is with safety, you kind of know what the knowns are, what the inputs are, what the output should be, what can fail, the single points of failure, and you can matrix that and do all of your tests and all of your analysis. When it comes to the security side of things, it's far less certain. It's certainly less known what you might be vulnerable to in the future. So one of the questions that we really all need to be asking, is our supply chain secure? Everything from the OEMs to the suppliers, those various vendors that are online, the telco companies, various device manufacturers, and of course all the tier one suppliers. And if you think you're secure, I think it's definitely something that you need to realize just how complex of a problem this is. And it's really impossible to be sure that you are. And you are only as strong as your weakest link, which is why each of us, as companies that deal with software, when we get deliverables from third parties, that we need to ask them, we need to be making sure that security development practices are in place and can provide some level of evidence that they follow them. And this is just a sample of kind of that big picture of what you're looking at. How many, at the bottom, we have a bunch of standards. This by no means all of them, it's just a fraction. At the top, you have all of the OEMs. On the left side, you have a bunch of companies that do hardware, software at various things, whether it's real-time operating systems, security products, voice recognition, navigation, open source products, closed source products. And then on the right side, of course, you have all of the, again, a fraction of tier ones that are out there. And all of this stuff has to come together and get integrated and delivered to the OEMs and ends up being put into the vehicle. And there really needs to be that supply chain of trust across all of these different players. In terms of Ricardo expertise, Ricardo is very well positioned to help our tier ones and our OEMs with respect to all of these aspects. We understand the mechanical, we understand durability testing, we understand sensor analysis, we understand what you can get from a development vehicle versus a production vehicle. We think we can get more data from that vehicle to better do analysis. Of course, we have the engineers that can do the analysis of the data and help our customers prevent future failures, at least have planned service times where if you can predict that certain events may be in a given vehicle's future, instead of being stuck at the side of the road with a breakdown event, that you can plan for that service when other services on the vehicle may also being done. And at that point, I think we'll head to the QA session and turn it back over to Marcus.
All right, for whatever reason, we're having a little bit of webcam issue here. But while we're sorting that out, so just a quick reminder, please send your audience, I ask you that you please send your questions through the questions tab or email the questions to us if you're watching from a pre-recorded version of the session. And then we will make sure that we get those answers back to you straight away. All right, so with that, let's go to our first question. So question came in from the audience, and I will direct this at you first, Pete, and then maybe Madison, you can chime in. Basically, we see that there is a tremendous amount of complexity that's coming in the way of this new goal to be connected. And one of the challenges that's inherent in it is that the data is siloed. How do we manage to get to a point where we have data centralized and we can take advantage of it in the face of these very linear approaches to how data is gathered inside of the manufacturers?
Okay, yeah, fair question. The data coming to the back end, of course, especially with kind of what we've been talking about with kind of this more flexible approach to collecting the data, targeting exactly what we want, getting that to the back end. At the end of the day, you could be talking about numerous types of engineers that may want to have access to that data. They have different roles and responsibilities, and there are going to be different kinds of analysts looking at that data. Some may be interested in estimating warranty costs. Others may be interested in solving engineering problems. So definitely you end up with a kind of a classic back-end application need where different people can have different types of access to that data and look at it from different points of view. I'm not sure that there's an existing solution for this. I certainly think vendors such as whether it be the Amazons, Amazon Web Services, Microsoft Azure, certainly those types of technologies and solutions would be a good foundation for trying to tackle that aspect of things. But in general, yes, that's certainly not a small topic or problem that needs to kind of get resolved. But I think it's probably more of a bit of a custom application on the back end. Different organizations are going to want to handle that topic in general, I think fairly uniquely and differently between them.
Okay, Madison, what are your thoughts?
Yeah, I think, well, I definitely see data centralization as one of the major issues because data is going to be coming from different types of vehicle at varying rates of accuracy. But also when you consider, okay, now you have all this data centralized, you have to optimize how much data that you've collected because you can have mass amounts of bad data that's not telling you anything. You need automated methods for analyzing the data so you're not having this mass amounts of manual engineering effort. And then beyond that, once you actually have the analysis and the outputs of analyzing the data, there's siloed groups within the OEMs that also need those outputs. So whether it's engineering or it's the production group or it's even the supply chain that needs to incorporate the outputs of that data into improving their own products. So, I mean, we need to solve the centralization issue, but it's also kind of this internal communication and process improvement for making sure that once the data is centralized and we have the analysis and outputs, that all members of the supply chain, but also the siloed internal organizations within the customers can effectively leverage the data as well.
Okay. So I'm going to build on that a little bit. So, I know that you recently did a webinar on digital twin, and this concept, I think, is very similar to the last question. We all, I think, as an industry, can recognize the promise and the opportunity of, this higher level of data activation. But how do we tie these two concepts together? Like you said, we've got a lot of different organizations that touch, manipulate, and use data. What does data activation mean in the context of digital twin or vice versa? Madison, let's start with you.
So really what differentiates a digital twin from purely a simulation or a model is the fact that it's updated with real-time data, right? So the physical asset is distributing its usage, its performance, and the digital twin is consistently matching what's actually happening in the real world. So data becomes data, and the accuracy of the data and the fidelity of the data that you're using to inform your digital twins becomes critical. And then, I mean, Pete went into the details of security aspects of it. We need to ensure that the points of connection in the vehicle that we're leveraging to pull the data are secure. So not only is the data from the car or the car's not hacked, but the data is not tampered with, so that the security or the quality of our digital twin is not compromised. So it's not really digital twin and or data, they go hand in hand.
Okay. So, so we talk about digital twin and being able to connect and access data. And I think it's very easy for us to rationalize that on, say, a new platform, right? But what is the opportunity for us to activate data on legacy platforms? So, I mean, because the reality is, you know, if I just take the passenger car space, what, in a bad year, we sell 15 million new in the US. On a good year, it's 17 million new. But there's hundreds of millions of vehicles already out there in the fleet. Is there a way for us to activate data from vehicles that are a year old or 2 years old, or or more? Pete, let's start that. Let's point that one at you to get started.
Yeah. Effectively, you have always access to your OBD port. The solution that we were describing, of course, would have to go through this, and really the ability to get closer to kind of that offboard diagnostics environment. We have certain types of solutions. Ford has their OpenXE, hardware, software, open source, hardware, software combination, which is directly was developed specifically so that third parties can use that technology to more easily develop applications. What data you're going to get out of the vehicle. Unfortunately, with most of the aftermarket devices, they're looking for very specific things, which is why I think that there needs to be an application that can be triggered more dynamically to target the data that is really being looked at when you don't really know what that use case is going to be. And in general, there's a lot of standards around these things. So, you should be able to develop a solution which is applicable to most of the vehicles that are on the road.
Okay. All right. So we're almost out of time, but I want to make use of the space that we have. Madison, a question for you. When I think about activation of data, in my mind's eye, I'm ultimately thinking about trying to find ways to new revenue streams, right? Today, you guys talked a lot about how we can deal with warranty and recall and mitigation of risk, I'd say, right? But what about tying in or finding ways to create new revenue? Do you have any thoughts on that?
Yeah, so, well, first, it's not just mitigating risk, but it's overall reduction of cost and reduction of downtime for commercial fleets. And then if you're looking at improvements of kind of driver experience, OEM brand image, the fact that we're enabling data to be collected remotely from these vehicles, and we have the ability to analyze it, we can track driver preferences, usage, we can deliver services, new functionality post-production at a premium. So you can take the Tesla Autopilot example. I think we covered that earlier. Tesla actually enabled their customers to purchase Autopilot functionality post-production at a premium. So you can either unlock existing functionality within the base software platform. Post-production, you can deliver targeted ads and services post-production as well. But you can also monetize the data that's being collected from the car, whether it's the driver monetizing their own data, whether it's the OEMs kind of leveraging the analysis and delivering targeted services to their customers.
Excellent. Pete, did you have any additional thoughts on that?
I think Madison's spot on. But at the end of the day, you got to be able to trust the device with which you're getting the data from, and even I think as we move forward with safety devices in general, not just vehicles, but I think especially vehicles with all of the autonomy that's starting to bleed into cars today, knowing that you're talking to the car you intend to be talking to, and even possibly using things like blockchain to maintain an unalterable history of a vehicle will also provide value, not just to a buyer, but to a seller as well. So I think there's a lot of technologies that will emerge from this that really aren't prevalent today.
Yeah, so just one thing to add, you mentioned, activating data for vehicles that are already on the road. And by activating data, it's not just monetizing services post-production, but it's extending the life of the vehicles that are already on the road, right? So if this existing production vehicle comes in, or the millions of existing production vehicles come in, and we are able to collect that data at a service bay, whether that vehicle is connected or not, we can actually analyze the data, do fault prediction, and optimize the maintenance strategies for either passenger car or commercial fleets as well. So you can update the maintenance training plans for your dealerships. You can inform the operators and owners of commercial fleets that, in 6 months' time, 50% of your vehicles are going to experience a failure. So why don't you mitigate that failure 3 months from now and save the downtime? So it's also about optimizing maintenance strategies and extending vehicle life for production vehicles.
Got it. So last question. So, and I'll aim this one to you, Pete. So I am an engineering executive, and I've been challenged by my leadership. Go find ways to turn data into value for the business, right? I can go very, very discreet in my approach. I can think broad. I mean, in totality, I can see where this discussion can become a very overwhelming task. Where would you start?
I think you have to maybe split it first into opportunities for direct revenue streams, new revenue streams, versus reducing costs. Reducing costs also can, of course, be not just the predictive maintenance, but taking the data and using it for engineering purposes for next generations of vehicles. Of course, making vehicles more reliable from having better access to volumes of data from actual customers and the way they use their vehicles. Just in general will enable you to develop better products. So I think there's not one discipline. It really is a flood of new opportunities. You're going to have, like Madison mentioned, you have new applications that you could purchase after the vehicle is already on the road. I know also some of the updates that Tesla has done has been improving the braking distance of a vehicle once it's left once it's been sold. That was a software update. So, how you promote your products, how you engineer your products, how you sell post-sale additional features. It's a very big topic. I think there's a lot of opportunity.
Well, guys, I want to thank you. I think that this was a great discussion, very informative webinar. I think what you touched on is a huge challenge and a huge opportunity for the industry, right? It's interesting because I often lamented that people using we use Tesla as a good example, and I think the benefit that you see is the art of the possible. It's always difficult for me, coming from a large OEM background, to think about scaling their volumes to the masses. But I think the discussion points that you guys covered today help us to get a clue into the fact that, one, it is possible, it's doable, it's been done, and two, that there's a path to do it. I thought your answer to the last question, Pete, was intriguing, because you actually really started with the use case, whereas in my experiences, we used to always start with the hardware, right? What was the component? What was the system? So you started with the story of what value we're trying to create. So thank you guys both. I think this was a fantastic discussion. I enjoyed it very much. For those of you who are watching live, Pete, please feel free to extend any questions to us that you might have. Our email addresses are on the screen. If you're watching this recording, likewise, the invitation is there, open to you. And we look forward to seeing you all in our next webinar. So stay tuned, because on August 26th, we're going to be talking about a holistic approach to thermal attributes and optimization of the system, energy management at a system level. So that one is sure to be intriguing and is very, very topical given the changes that we see in our product portfolios as we look to the future. Thank you all, and we hope to see you again soon. Take care.
Thanks, guys.
Thank you.